So we're going to move to the next unit, which is about places, and talk about places are actually a different name for evaluations. And in Stichtonov's book, places is actually the maximal ideals. So it's, sorry about that. It's all equivalent, so you can choose what you want. I'm following more Dan Aran's notation than Stichtonov, so places for us are going to be what we are going to define now. Okay. So for a moment, forget about valuation rings and their maximal ideals, and let's do places now. And then we're going to connect them, so only for a moment you should forget about it. And before we start, we need to do a little bit of a technicality. So I'm just going to do that. So we are in unit 6 or something. Unit 6, places. And I think of all of this as a place, right? Not really a point, but it's a place. I forgot the notes. And places, in order to talk about them, you have a field. This is, so this is, I mean, it's a field. I don't care. I want to write something like formal. But when I write K here, I really mean the field of things that you get after you evaluate, like F5 or something. For me, this is now F5, not capital F, which is the field of functions, but just a small field. It doesn't matter for the definition, but just so that you'll have the same like mental picture as I have. So what we want to do, I mean, if you have a rational function, you can say, I can either, and that's what we did here, I can either restrict to the domain of that function in which it's defined and stuff like that, or an alternative approach would be, and it's kind of less popular approach, would be to say, I'm going to let it be defined everywhere, but I'm going to kind of spit out abort when it's not defined at the point that you are trying to evaluate it. Sometimes this perspective is more useful, and sometimes that perspective. Sometimes you want to keep the domain as is and allow kind of abort symbols, and sometimes you, well, that happens like like when you do Hilbert spaces and stuff like that. And sometimes you prefer to kind of restrict the domain and not have abort symbols. And that's what you usually have, like in complex analysis and stuff. You look at the domain of the function and stuff like that. But here, for the notion of places, it will be useful to do the abort symbol, and we are going to call the abort symbol infinity, which is very confusing because it's not a big number. It's just like, I don't know what's going on there. It could be a negative number. It's a pole, really. Here you have only poles, so no other singularities. So say you have a field, we adjoin K, an element, which we denote by infinity. It's a very different infinity, for example, than the infinity of valuations. Valuation infinity tells you, only 0 gets the infinity valuation. Valuation sends only the 0 function to infinity, and by that it tells you infinitely many zeros. This infinity just means a pole. There is a pole there, so it's a different infinity. Okay? And it will never be in the same context, so that's obvious, but just to make sure I understand it, we adjoin and extend the field operations in the natural way. So I'm going to just write everything, but So for example, for every element in the field, A plus, I want to kind of add a new symbol and add and subtract and multiply and divide by. So when I add or subtract an element in the field with infinity, I get infinity. Okay, it's like undefined plus defined, it's undefined. And it's also like minus infinity. I mean, I need to define minuses of stuff, so it's undefined. I don't care if the pole goes like this or like that. Yeah. And it just, in case you wonder, it's commutative. I don't know, like that. Okay. And so that's a rule that kind of conforms with a pole. It's undefined. If that's not defined, then that should be defined. And for every A that is non-zero, the same happens with multiplication. Right? When you multiply a non-zero with infinity, you get infinity. With 0, it should be undefined. And you multiply infinities, or you multiply an element from every side, it should be infinity. For every element in the field, including 0, what will happen if I'll divide by infinity? Get 0. That's kind of fun. It's undefined, but we can still say something, right? We can say that it can still take a field element to a field element if you do that. You kind of feel like something weird going on, right? Like, you don't feel it's kosher like to do these things, but it's fine. And when you divide non-zero elements by 0, like this is kid stuff that you teach them not to write that. What do you get? So infinity is a number. They lied. And just to make sure that we understand, like some stuff are not kosher because they depend on rates of how big is the thing is. And I'm not sure there is a big because it's like FQ. So these expressions makes no sense. I mean, we still need to kind of be like, I don't know, consistent with things. So you cannot do that. You can't add infinity to infinity because infinity could be minus infinity, right? Here I added only like finite to infinity. Infinity minus infinity is not 0. It's like, you know that. And you can't multiply 0 by infinity because, L'Hopital rule will tell you who wins or something. And infinity times 0, and 0 times 0, of course. This is what has nothing to do with infinities, and I don't know. It's just to make sure that you're not going to use this in a non-kosher way. And infinity over infinity. None of these makes sense when you can't do arithmetic like that. But you can actually add the infinity symbol with these rules, and they are consistent. Nothing kind of breaks down weirdly, and that's the arithmetic that we'll use. Okay. Right. Which one? This one? Ah, right. Because because 0 times infinity doesn't make sense. Because like infinity is undefined, so maybe this is 1 over x, and maybe this is x, and at 0 this is like 0 and this is infinity, but x times 1 over x is 1, but x and 2 over x is 2. So you can't, I mean, if you have a function that is 0 at the point and a function that is infinity at the point, the product is, you can't really define it in a consistent way. Because, for example, x and 1 over x are examples. One is 0 at the point, 0. The other is infinity at the point. The product is 1. But 2 over x and x, the product is 2. So you can't be consistent doing that. And also here, in this case. But just take the other way around. Like 0 is 1 over x and a is x. Yes. So that's why it's a problem, right? Yeah, exactly. So that's why. So that's like a not info, like a bad definition. Oh, sorry again.
You said there that infinity is negative infinity. You said that like infinity minus infinity isn't defined.
Right.
But if you define infinity to be equal to negative infinity,
Yes. It's undefined. This is like 0. I mean, just here I'm saying that 0 minus infinity is infinity. If you want. I'm not saying infinity plus infinity is something. Or infinity plus infinity is something. Are the same. Yeah.
same infinity plus infinity is undefined.
Yes. You can't like subtract minus infinity from both sides. You're trying to say this is contradicting because you can reduce minus infinity, but you can't. Because I told you that you can't. I'm consistent. This has been checked.
No, minus infinity is not the additive inverse of infinity.
No, it's a. That's a good. So right. So that's the essence of the question, right? So here I'm saying like this is its own like additive inverse. I'm not saying that. I'm not like filling the entire additive addition table that is completely defined in the field itself. I'm just saying that there is infinity. There are, by the way, there is also 2 times infinity, this thing. So so you can ask, why is this not like infinity plus infinity or something like that? So I'm just saying that I'm defining this symbol. I'm extending the minus operation to satisfy that, but I'm not allowing you to add or subtract infinity. So there is a missing like tables, cells in the table. And it is consistent, but it's kind of, there are missing parts. It's not fully defined because you cannot fully define consistently. But that's fine, I'm allowed to do it.
For the additive inverse with the unary function that is no longer the additive inverse.
Exactly. So the minus here it looks the same as I'm extending it like that, but I'm not extending the addition or subtraction to infinity times infinities.
It's the natural way of function. Like the infinity of R is what we expect.
Yeah.
But we just never
and minus R.
Never noticed that infinity minus infinity are
the same, exactly. Yeah. So in R it's like this, it's the same thing for me. And also in C, in all directions. Yeah, exactly. So that's really what's going on here. Yeah. I know it's weird. It's weird, like, because you need courage to like, yeah, but you lived like 24 years. Okay. Oh, I wish. Sorry. Yeah. So you live your life, and they tell you initially not to do those things, and then you learn a lot of math, and you still don't do those things. So you kind of expect, they were right. We shouldn't. And then someone comes, and like still young, comparable, not like an old professor, famous professor, and it tells you, no, it's fine. Don't worry about it. You can do it, and it makes sense. No worries. But it is fine. It's not that me that told you that, right? I'm just kind of communicating what the elderly told us. Yeah, it's just a convenient way of saying things. That's it, really. But really good questions. So with this, where is the? Oh, yeah, 4, 5. So with this, we can finally define the notion of a place. So definition 1 in this unit. So again, everything here was not, like the infinity 0 were not function. This was the answer to evaluation, right? So now you'll see what I mean in the definition. So let f and k be fields. This is like fields of function, and this is f5. But it doesn't matter for the definition. A map, really an evaluation map. So P from F, it takes a function. There is a point in the space somewhere. You take a function and you produces an element in the field in F5 or above infinity. Right, so that's evaluation. But everywhere with this new symbol is called a place. If, and now you just need to make sure that you are consistent with the infinities. So let's do it. Because I'm defining it everywhere, and I want to be sure that my definition is okay. So you need 3 things. So first of all, just P of 1 is 1, that's nothing. Like the constant function, the one constant function always outputs 1. Don't worry about that. Here is more interesting. So when is phi of A plus B? I mean, you want it to be what, usually? Right, because you evaluate a function at a point. So these are the functions, right? These are the points. It's kind of funny. So you evaluate a sum of functions on a point. It should be the sum of the individual evaluations, if you can, right? So, and you should think hard, but then what you get about if you can is whenever at least one of them, one of the individual, the marginals, is not infinity. That's the right thing to do. Yes. Exactly. You should think of f as like the f5 of x, and this is f5, and now like 1 over x at 0 is infinity, but otherwise it's like the inverse of 5. the number that you get. Exactly.
But P of like normal A can be infinity? I mean,
Yeah,
but so if,
but not both. Like,
no, I mean, okay, I got it.
okay, but let me. I do want to say it. So there are three cases here, and I omitted one of them. The first case is that both P of A and Phi of B are not infinities. So I think of it as like functions that are defined at the point. So definitely their sum should be defined at the point. And that's just, you don't involve infinities. That's fine. So if both Phi and A and Phi of B are non-infinities, I mean, you want that rule. I mean, if you evaluate two functions that can be evaluated, their sum should be possible to evaluate at the point. So the rule should kind of confirm that. If one of them is infinity and the other is not infinity, that's also fine because you know what should happen. You should also not be able to evaluate. Right? If you add 1 over x to a polynomial, it's still not evaluated at 0. Right? So that little asterisk about only at least one of them is required is kind of part of the way we think of evaluation. Right? But indeed, if both of them are infinities, then it's, I don't know, maybe this is 1 over x and this is minus 1 over x, and then it is defined. Or maybe this is 1 over x and this is 1 over x, and it's not defined. So I don't have enough information. The evaluation function doesn't have enough information to argue about it, so it's not defined here. I'm not even defining this. I don't require this. Okay? Yeah. It's whoa. It was harder than expected. And as for product, well, it should be the product. And here, I mean, here also 0 is an issue, right? I mean, if one of them is 0 and the other is infinity, it shouldn't be defined. But if both of them are infinity, it's fine because infinity times infinity is defined. It's like you know that when you multiply two infinities, it should be infinities. Like, so the only problem is that, like, let me write it like that. The only problem is that one of them is infinity and the other is 0. Because if none of them is infinity, it's fine. If one of them is infinity and the other is either infinity or another number, that's fine. The only problem is 0. Because you can't do this with a 0. So these little rules that's exactly the right notion of an evaluation with poles. Yeah. Thanks. All right. Good. So that's I mean, that's a definition. You don't, but that's the right. I mean, I'm going to prove equivalences, so that's a right definition. So clear, it's the right definition. Yeah, right. So I call it evaluation, but yeah. So you evaluate at the point, you evaluate the function at the point that this encodes. Exactly. Yeah, precisely. And there are a couple of examples. I feel like I should at least say one of them. So, okay, so I have to do it. So there is one example with prime numbers, and there is one example with polynomials, and I'm just going to do the polynomials one. Just because of time considerations. So you do understand that we are really at the very beginning, right? It's like we haven't yet fully defined the notion of a point. And this is a course about curves. So it's like it didn't even start, and it's really going to be interesting afterwards. Like I think the next lecture is really the beginning. But yeah, so this is kind of the basics. So hopefully it's not too boring. But so let's see. So just as an example, I mean, it's an example, but an important example. So say you have E is a field. Why did I call it E here? Yeah, okay. So E is a field. I think the better name would have been K, but E is a field. And you take an irreducible polynomial over the field, okay? And now what I'm going to do, I'm going to define a place, but I'm going to do it in 2 steps. So first of all, I'm going to look, the point is to define a place that corresponds to this polynomial. So the first thing I'm going to do is to consider the projection map. We talked about it in informal expectation. We talked about it in informal discussion. So this is the projection map, right? A polynomial is sent to the coset. Okay. So here there are no infinities. And what I want to do now, so if we call this thing L, that's a field. Oh, that's why I didn't call it K. That's a field because this is irreducible in this ring. So, and this is a UFD. So irreducible means that when you divide by it, you get a field. It's a maximal ideal. You get a field. So this L, that should be the good name for that should be K, but let's call it L. So now that's not a place. A place is from a field to somewhere, and this is from a ring. So I'm going to extend it by extending this to the rational functions in X to L union infinity in the natural way, namely, given f of x, you write it as a of x over b of x. Every element here looks like that, right? You do the co-prime stuff, it looks like that, and then you send it to either, you send the numerator and denominator according to psi, or as long as p does not divide b, and that's therefore is not 0, or you send it to infinity otherwise. All right, so what did I do here? I told you how to evaluate polynomials, and remember that doesn't look like an evaluation, but we said that's an evaluation. That's an algebraic way of considering evaluations. And then there is like one way to extend it to rational functions. You just evaluate each of them and divide in this field as long as the evaluation of the denominator is non-zero as an element in this field. So as long as, in this case, p doesn't divide b, because that's the only reason that you'll get a 0 here. So that is a place. I mean, you should check all the stuff like that, but no one ever did. And in the particular case where p is like x minus alpha, like in the case that you are used to, that doesn't look like an evaluation. But what I'm saying now is that if you just consider the special case where the irreducible polynomial is x minus alpha, where alpha is just a point in E. So when p of x is x minus alpha, what's going on? Then let me do it here. So when this thing is x minus alpha, this thing is really what? Like, what can you identify it with? F of alpha. Right, I mean, technically it's f of x plus x minus alpha, but there is the quiet homomorphism that just maps x to alpha and does that. And then this thing is a of alpha divided b of alpha, provided b of alpha is non-zero. So let me write it, but so then phi of f, phi of like a over b is just what you would think, a of alpha over b of alpha. Again, this is kind of identifying. I'm writing into feed element, which is like isomorphic to E, where I should write technically a coset. But you can't do that. You can't live like that. You can't always write the cosets. You really need to understand what to omit. Like when you do it here, you also do it. Like you don't write the coset of all rational functions that are equivalent to that. You just work with a representative, and this is a good representative for the class. So you can write it like that, provided b of alpha is non-zero, because this is equivalent to saying x minus alpha doesn't divide b, which is what's written there, and infinity otherwise. That's what you want, exactly what you want. Yeah, right, I'm doing only AB copine here. So I chose a representative. So you can always bring it to that form and then do the job. Interestingly, by the way, when you work with on curves, you don't have the luxury of doing coprimeness because you don't even have UFDness in the polynomial level. You can't factor out things uniquely. But the definition of a place still makes sense. It just generalizes this situation. So in this situation, I can do the coprimeness, and then it kind of touches what we are used to, and you can do that. On curves, you cannot do it, but places don't care. Still a good definition. It's really the good part about it. Like, it kind of is detached from our previous experience in the right way. Yes.
Why do places call these places?
Right. So I think the point, a point was a good name, like point, because it corresponds to points. But really, you see here, like alpha is the point that corresponds to x minus alpha. But you can take any irreducible polynomial. And if you think about what does it mean, really, I mean, the only reason you have an irreducible polynomial which is not of this form is because that your field is not algebraically closed. Right. So what I'm saying is this place kind of generalizes the notion of a point. So in what sense? I mean, all of them generalize the notion of a point, but from this definition, you can see it more easily because you would agree that when P of x, in this particular example, when P of x is x minus alpha, it captures points, like evaluation at points, but it captures the notion of a point. So what is a point if not evaluating at? See, so what is a point? Like the 2, 4? That's coordinate dependent. That's actually a bad definition for a point. Right, so you live in your... Right, or all the functions that are 0 at the point. So you define point how the world conceives it. Like 2, 4 is a bad notion of the definition of a point because it's coordinate dependent and stuff like that. Like if you are like a little ant that sits on a curve, you don't know that there is like a coordinate system around you even. And there shouldn't be. Exactly. So you try to kind of intrinsically define the notion of a point. And like in other areas of mathematics, the way to do it is to see how operations, usually functions, behaves when related to you, when either evaluated at you or when functions are defined at you and so forth. So you find all of this, how the world perceives you, and then that's you. Yeah, and that's one of them. The other is the O and the M. These are the places. This is one way of doing it. Right, and all of them are equivalent, which means that they capture the same thing. It's a philosophically very interesting point, like message. But here you can see by more concretely, and then we take the break. The point alpha does correspond to this place in the sense that from this place I can figure out what alpha is if I want to. But other things are also encoded, like all irreducible polynomials, really. You need the irreducibility, otherwise you're in trouble. You don't get a field. So all the irreducible polynomials, and what is an irreducible polynomial? Just a conjugate class of points in some field extension. So a place is really either a point or clouds of points. And we will see that, but like in F, like x squared plus x plus 1 is irreducible over F2, but it does corresponds to 2 points in F4. And F2 can't separate them. Polynomials in F2 cannot separate them. So it's like a place is really either a point where the polynomial lives or clouds of points above where the polynomial lives. Yeah.
Not in the larger place, it's actually a location.
Right, exactly. So if you extend the field, it's actually a point there. So a place is... Right. Yes, right. So in the field extensions, but without omitting the fact that they are the same. Like from the F2 point of view, these 2 points are the same in F4 and so forth. So they're clouded together, like in a sense. Okay, but let's take a break and we can talk about it offline. And yeah, and we'll continue from there. Yes. So like with evaluations, actually the right thing to do is to look at equivalence classes of places, because there are like too many places that give you the same information, so you want to mod out by that. So two places, and one of them is maybe from F to K union infinity, and the other is from the same F. I mean, you're talking about the same function field, but maybe they send it to, you know, another field of answers. We're going to call it a residue field at some point, but a field of answers, like where the answers lie, are equivalent. Any guesses? Exactly. So you just care about where things are defined, not what is the answer. Usually, like in what happens from before. I don't know what I had, not equality, it's with equality. But two places are the same if they agree. Maybe they send things to different fields, but they agree on which functions are not defined at the point. Okay, so for example, just so that you'll see that that's the right kind of definition. So if you take alpha and beta in K, distinct, and you take the place of evaluating at alpha, as according to what we did. You take a rational function, so you consider both phi alpha and phi beta from K of X. So the F now is the rational functions, like in the example. The answer should be, I mean, you're going to evaluate the field element. So it's a field element or, of course, infinity. But I'm going to look at the natural one. So like phi alpha is just plug in alpha. Phi beta is plug in beta, evaluating at beta. And I claim that they are not equivalent. They shouldn't be equivalent. These are different points, alpha and beta, and they are not. Because, for example, phi alpha, I mean, give me a function that this is infinity, but for the same function, this is not infinity. Exactly. This is like, in a sense, the canonical answer to the question, what is the simplest function in which this is not defined there? We are going to call it a local parameter at some point. So there is a name for that. And this is, and this evaluation at beta is just, you know, beta minus alpha 1 over, that's non-zero. It's not infinity. But technically, it's like really 1 minus beta minus alpha, 1 over beta minus alpha, which is the field element. We assume they are distinct, which is not infinite. Good. So, I mean, so I don't know what but this is an example of just showing you that we didn't mod out by too much. Like different points can give you different valuations, places. And the same holds for more general settings, of course. Right. It's also good. So even if I take a phi of a reducible polynomial and another reducible polynomial, it's also not the same. Because you can look at 1 over that irreducible polynomial. I mean, this is really the polynomial that corresponds to alpha. So what I'm saying is that if you take alpha of x and beta of x, just to keep the name kind of similar, to be distinct irreducibles in K of x, then it's also true that phi of alpha is not equivalent to phi of beta, because phi of 1 over this one applied to 1 over alpha is infinity. Exactly. When the 1 overs are like not defined there and they are defined here. Okay, so I'm going to kind of state a couple of claims without proving them because they're so easy and really boring. What they really do is just case analysis. What happens if one of them is infinity? Or it's really boring. I did it last time, and I think that I think maybe Itai were there, and I remember you told me no, don't do it again. Just next time, just don't do it, and I'm going to listen to your advice. And so you should thank Itai. I mean, it's also, you can't really follow someone doing that. You just need either to do it yourself or just never see it. So here are some obvious stuff. So let's say you have a place then some obvious properties. So the first one is, what is phi of 0? What do you think it should be? It should be 0, right? And in the definition of a place, you don't have that. You have phi of 1 equals 1, and then you have the phi of AB is phi of A, phi of B when conditions are allowing that, and phi of A plus B is phi of A plus phi of B. You don't have that, so what you do is you get phi of 1 minus 1. Okay? And then you do this, because 1 minus 1 is 0. So that's obvious, but I just needed to just mention that. So phi of minus A, well, the valuation of minus A is just a valuation of A. But phi is something else, right? It's evaluating. So what is phi of minus A? Minus phi of A, right? Because if you take a polynomial and evaluate it, and it's minus, and you evaluate it, you get the minus evaluation. Take the minus of the polynomial, not the minus of the point. So good. So I'm not sure why I wrote that. I don't know. I mean, okay, here is another thing. Okay, I guess it's not immediate from the definition. So if phi of A and phi of B are both of them not infinity, you can look at phi of A plus B, and kind of obviously it won't be infinity. Why should you get infinity when you like not there? Anyhow, that's obvious, and that's the only thing that's maybe worth mentioning like explicitly. Maybe next time I won't even mention. So what can you say if I'm telling you that phi of A is infinity? What can you say about phi of A inverse? Exactly 0, because the only reason a function is infinity, a rational function, is that its inverse is 0. Right, when you evaluate it, it's like yeah. Why should a rational function be infinity? It's because the denominator is 0 at the point. So when you invert it, you get the 0 towards, like in your favor and not against you. So you get a 0. Right. So that's an exercise. You can look at the notes, but it's actually better to maybe just do that or something, just to get a feel. But you don't want to see me do that.
Said that plugging into a polynomial inverts the sign, but like x squared, how does?
Right, but look at the polynomial minus x squared. Right, so I'm inverting not x, not the input to the polynomial, the polynomial. Right, so that's because this is the function that you are evaluating. So this is like maybe minus x squared, and this is indeed minus x squared. Right. So it's not the input, it's the output that you're inverting. So there is a definition and a claim. I'm just going to combine it together because it should have been like that from the get-going. So claim 7 plus definition 6. It's kind of a definition you can only do once you have the claim. Anyhow, you'll see. Oh, sorry, it's I think it's like 5. I got lost. 18, 19. Where is 20? 19. Oh, this is 20. So I need 21, 22. Wow, it's the same picture. It confuses me. But yeah, it's fine. Claim 6 and definition 7. Yeah, good. So, okay. Let me just do definition. Let's call it definition 6. So that's what's written. I'm just copying what's written as definition 6. So let's say you have a place. Right, so 1 goes to 1. In addition, multiplication behaves nicely with infinity. Then the field, and the fact that this is a field is a claim. That's what I mean. I'm going to write a set. It's going to be a field. So this is claim, which is written before the definition. But I'm going to write a set. That's going to be a field. It's easy. So the field, which we denote by f bar, which what you do, you just evaluate phi at all of your functions, and you just ignore the infinity answer. I mean, you just collect all the answers that you get other than infinity. Like usually, if usually you kind of get k, unless something is weird. Like usually, when you write polynomial, you get all the answers from there. But maybe you did something like weird, and okay, it's called the residue field of phi. I'm going to draw a picture to explain this, and it will be more. This is like the field of answers. So what do I mean? So you have f, you have all of your functions. So think of it maybe as rational functions, right? And then phi maps it like technically to k and infinity. This infinity here. But really, you may not reach all of k. That's what I'm saying. I mean, maybe these are polynomials over f5, and for some reason I put f25, right? Kind of artificially. So that's still a place. I never require it to be like onto in any sense, but it's not like it's just redundant. So f hat is this thing, which is really, everything that is here that doesn't go to infinity. Right, so that's what's written there. P of f minus infinity. So all the evaluations that you can actually get. So again, if this is a polynomial over f5, and you're just going to put f5 here, and then indeed you can get everything. But if this is a polynomial over f5 and this is f25, and phi doesn't allow you to plug in things that are outside of f5, when you won't get f25, right? So that's just kind of saying sometimes this is redundant. Like in the evaluations, like the ordered group could have been larger than the actual image. And I'm just kind of mentioning that here. So that's that. And the fact that this is a field is kind of obvious. Like you need to check that if you can get two valuations, then you can, like two numbers, you can get their sum. But you know what to do. If you get two valuations, you can find a function, the two functions that give you those valuations, add them up, and that will give you the sum here. And also the product. So it's a field by definition. And I think that, right, so the claim is that, no, so the claim is a good claim. So with that, we are ready kind of to connect places with valuation rings. We are going to do this. And because these are connected, we are going to complete the picture. Okay.
All the values that can be given.
Exactly. So like if these are rational functions over f5, some of them will go to infinity at the point that you have in mind, maybe the point 0. I mean, the point is fixed by the place. So some of them will go to infinity, but the other will go to the field elements that you're evaluating according to where you evaluate your polynomial, and you collect all of those, and that's your field of residue field. So in the field of answers, we call it of evaluating a function at a point. Because phi evaluates a function at a point, given the function it evaluates at the point in which it's kind of trying to abstract. So you get all the answers to all the questions, what does this rational function say is evaluated at 0 and so on.
What is the, sounds very
so for example, in coding theory, that's where the code is going to live. Like because you're going to evaluate functions, you're going to get symbols, and that's like the field in which the output of the field is going to live. Right.
Which is the possible values of functions over this place.
Exactly. And every place is a different coordinate in the code, because you evaluate at different points and places. But you will see its relation, like coding aside, you will see its relation. I mean, that's the right information in order to connect it to here. I mean, in a sense, k is not important. What is important is really the residue. K is like, it's like the ordered group that appears if.
Because it's fixed place.
Right. For different places could have different residue fields. And we call them, by the way, residue fields because it's like the residue. And if a polynomial, what does it mean to evaluate at alpha? It means you quotient out by x minus alpha and look at the residue. That's the answer. So that's why it's the residue field, the field of residues when you do the quotients. Because evaluation is taking the residues. Right. So that's the name, the source of the name. And I think this part is going to be insightful because the relation between all of them is good. So claim, no, here it is, claim 7. So let's see. So now I'm going to go from a place to evaluation ring. Okay, so let phi, so it's a place, so it looks like this. And again, place means 1 goes to 1, and addition and multiplication are nicely behaved. It's like essentially the evaluation homomorphism, but with infinities also. Like phi of a plus b is phi of a plus phi of b, phi of ab is phi of a phi of b, but with the infinities playing nicely with each other and with the field elements. So, right, so now there is an obvious way, if you really got it, to define what are the functions that are defined in this point that we think about, given the information hidden in place, like in the evaluation. So I'm going to just write, I'm going to ask you, but I'm just going to do this. Which are the functions that are defined? Exactly, right, those that are defined. Right. It's that simple. So, I mean, if we have the definition sets up right, then this should be evaluation right now, because yeah. So yeah, so it's actually a very boring proof. So proof exercise. I mean, the other directions are more interesting. I mean, what do you need to check? What is the claim? It's evaluation ring, yes? So I forgot to write what the claim is. Proof of what, right? Is a valuation ring with fraction field F. It's really easy. I mean, for example, just as an example, I mean, you should check, it's closed under addition, multiplication, but the interesting thing is the valuation ring part, like either A or its inverse is in the ring, right? So I mean, part of the proof sketch, I mean, the only part of the proof that's interesting is saying why A or A inverse should be in O phi. But if A is not in O phi, it means that phi gives it infinity. And then what does it phi of its inverse? 0, right? Because the only reason this is infinity is that this is 0. In particular, that's for the point number 4 here. In particular, this is not infinity, so it's perfectly matched to work. And there is absolutely no reason to see the proof. There is a reason to do the proof, to try it, but not to see someone doing it, because it's very easy, and it just kind of a good practice to see that you got the definitions. Yeah, it's going to happen. I mean, we're going to do it right. So what this does, it takes a place to evaluation ring, and from that you can get evaluation. But I mean, well, that wasn't a very easy error. So I don't know how to tell you exactly what the thing. I mean, I know the proof, and I still don't have an easy way of saying that. Yeah. Right. It doesn't. Valuation tells you. It seems like more information. Valuation tells you what's the order of 0 that you have. And it's not clear why, but I mean, an evaluation ring, and definitely that, only tells you if, if it is a zero or not. It seems like a weaker information. It's not graded. It's like pass or fail versus the actual grade. Like x squared and x are considered the same here in a sense, and they are different here. But actually, there is enough information here to get that. Because from the evaluation ring, that's a great question. From evaluation ring, you can get the maximal ideal, and the largest power of the maximal ideal, like when you multiply ideals, is really the multiplicity, is the answer to what is the evaluation. This kind of hides in this arrow that I'm not doing, but in a non-explicit way. So it's not like you see it. Maybe you can do that more easily in that sense, as you maybe suggested before. Because that I can tell you. That's kind of easy in a sense. Like from the maximal ideal to go here, I'm just checking what's the largest power of the maximal ideal that the function still sits in, and that's the valuation. Yeah, but that's a good question. All right, so I just don't have all the time. I mean, we have so much to do, and I have to skip some, and that's going to be skipped. So this is just to have the full picture. O phi is all A in F, such that phi of A is non-infinity. The other direction is more interesting, so I'm going to do it. Like how from evaluation ring you're going to get, like how from evaluation ring, it's a ring, you're going to get a place which is a function from F, which I know, to a field which I don't know. Right? So it's like to go to the evaluations, you had to cook up an ordered group from a ring, which is not clear how to do. And here you have to cook up a K, or really the residue field. And it's not obvious how to do it. It's more obvious, but it's not obvious. But before that, let me just say one more claim about the units. Just want to relate the units. Most of these claims we're actually not going to really use, but it's like not telling you the story. So claim 8. And even if we are going to use them, it's kind of be obvious to you. You forget what we proved and what just proved. So let's say P from F to K union infinity is a place. Then, okay, so let's do it. So how would you characterize the units? The elements here are those that don't get infinity. Here I'm asking not what are the elements that are defined, but also from those, what are the elements that are non-zero? Oh, did I just, yeah, that's fine. I just ruined it, right? I just ruined I gave an answer. Oh, because it's the same thing, so we can. Because an element here is invertible exactly when the evaluation is non-zero. Because when the evaluation is non-zero, you can invert the function and then evaluate. So, sorry, it's the same thing. Another way of writing it, of course, is all functions like taking the non-infinity and put it like as this condition here. And that's just obvious. Instead of writing not infinity explicitly, I just wrote it here. But the reason I write it like that is because now you can see that it's just exactly the ring minus the kernel, which is kind of, I don't know, nice. So the kernel of phi is exactly those things that you should remove from the ring to get the unit. And you know that there should be a maximal ideal. I mean, you know the relation. So the units were defined like before as, the ring minus some, like the maximal ideal was defined like the ring minus the unit. So it all makes sense. Like before we defined the maximal ideal. I mean, we didn't have to define it, it was there, but the maximal ideal was given by the ring minus the units. And so it's not surprising that if everything is equivalent, then that should hold. Something like that should hold. And I'm not going to prove that as well. It's easy. Actually, there is, I think, almost like really nothing to prove. What can you say about equivalent places? I mean, I'm trying to go to that arrow, but really it's going to be congruence classes of places, like here. Even though I don't have an example of two places that are equivalent that are not the same, I still have to, I mean, there is such an example. There must be. So in order to get the arrow from congruence classes of places to valuation rings, we need the following little claim, which is also obvious. So let's say you have two places. Let's just do that, okay? I'll do that. Then what I'm claiming is that they have the same valuation ring. That's just by definition equivalent. Because equivalent means that they agree on who is infinity. Right? So the proof is like, it's obvious, but maybe just me write something. So O phi is all A in F for which phi of A is non-infinity. But because P and phi prime are equivalent, you can just replace phi and phi prime here. Because equivalent means that they point at infinity at the same time, which again is just by the same logic, by the definition is of pi. Right. So then you have this theorem that we're actually going to prove, like, you know, most of it. There's always the annoying part that tells you this arrow. How you go from a valuation ring to a place. Or really from a valuation ring to a congruence class of places. Like it's going to be a place, but the one-to-one bijection will be on congruence classes. So that's actually is a kind of, it's declared to be a theorem. Theorem 10. So the map that sends the map that we said that sends a place to a valuation ring, but I'm taking congruence classes is a bijection, namely I should give you the inverse, a bijection between the congruence classes of places of F and valuation rings, again with the asterisk that with fraction field F. I mean, you always need information about where you live. So what I claim is that this bijection, which I defined from a place to valuation rings, but because equivalent places actually go to the same valuation ring, it's well defined to do it over congruence classes, right? Because equivalent one goes to the same thing. So really it's congruence classes of places. Much like here. So that's not obvious, not completely obvious. I mean, the obvious thing is that it's, I mean, it's sort of, it's the obvious thing is that it's really the claim there. It's well defined, like phi and phi prime in the same congruence class go to the same valuation ring. So this map is well defined. That's proof now. So well defined by this claim, right? Which tell you that you can take different representative in the same class, you'll get the same valuation ring. And the one-to-one is also obvious. Because if you take, but it's a different only. If you take two places that are not equivalent, it means that there is some A for which one tends to infinity and the other doesn't tend to infinity. And that's reflected in the evaluation rings. Evaluation ring will be different. In one element, it will be, that's yours, right? Yeah, sure. In one element, it's going to be, one element is going to be in OP and the other is not going. The interesting part is onto. And that's what I said. How from evaluation ring you can cook up a place, right? And in such a way that when you compose it, you get identity, like it's projection. So the hard part is, just to think about it, a place, you need to kind of compile the definition. A place needs where to go. Like it takes a function and it needs a place, like a field to go to, not a place, a field to go to. But what could be this field? Because if you take two distinct places that are not equivalent, then it means that there is an element because of which they are not equivalent. Right. Exactly. Right. One place sends it to infinity, the other doesn't send it to infinity. And then there is an element in the corresponding ring which appears in one and doesn't appear in the other. This is an if and only if. But let's do the onto. The onto is interesting. I mean, how can you cook up a place from evaluation ring? And as I said, you need a field of answers, and you only have a ring. Or do you? Like you have a ring and what else immediately have? Exactly. If you have a ring and a maximum area and no idea what to do and you want to get a field, you quotient, right? And actually that is exactly what happens in the examples. But so here is the proof. So the idea is like, let's let M. So again, we are starting with maybe let R be evaluation ring. I want to get a place, and I want to get a place in such a way that, this is a bijection. So let M be, it's unique. I mean, it doesn't matter for this definition, but it's unique maximal ideal. As long as it's maximal, I'm happy. Then define K in the sense of like residue field, that will be the residue field, to be the quotient. I mean, that's how you define. Like we said that to evaluate, you quotient out by M, in the examples, by X minus alpha or by. So that's exactly what's going on here. Like, you tell me which functions are defined, you tell me which functions are zero, and then quotient to get all the possible answers. But I'm just defining it, okay? And then from this, I'm going to get the place. So like in the example, we start by let psi be the projection map. Right, so this is K. Be the projection map, right? An element is sent to its coset. That's evaluation of polynomials in a sense, right? This R is all the things that you like in the informal level. R is all the things you can evaluate. These are the evaluation outcomes of the things you can evaluate. Like projection is evaluating. But I don't want that. I want a place. So it's something from the field of fractions of R to that. So I'm going to extend it in the natural way, right? Because R is evaluation ring with field of fractions F. So extend P to, let's call it psi to, let's call it phi, or I still call it psi, to F by as follows, by setting psi of A to infinity for A not in R. Right, so if A is in R, I'm already defined psi, and now I'm extending its definition, keeping the same name, and sending everything in F that's not in R to infinity. At least that has like the structure of a place, like at least psi now, the new psi goes from F to K, this K, union infinity. We need to check it's a place. And we need to check that if you take that place and go back to the evaluation ring, you get the same ring that you started with. So let's do some of that. But it all kind of makes sense if you have the story in mind, like the motivation, the examples. So let's start by let's try to prove. I think it's like maybe not so obvious. So I mean, we need to show it's a place. So we need to show that psi of 1 is 1. That's obvious because 1 goes to 1 plus m. We need to show that psi of a plus b is psi of a plus psi of b, including all the infinite issues, and also the phi of ab equals phi of a, phi of psi of e, psi of b. And then technically we also need to check that it's a bijection, not just like the inverse, like you go back and forth, you get the same thing that I'm not going to do. But let's just do the one thing. Let's take two elements and let's show that psi of a plus b is psi of a plus b. And we don't have to do it when, I mean, we only have to do it when at least one of them is not infinity. That was part of the definition. We didn't require that from the definition of a place when both of these are infinity, because it doesn't make sense to ask us this question to begin with. So whenever at least one of psi of a and psi of b is not infinity. Because if both of them are infinity, you ask me the wrong question. It's not part of the definition of place. And there are two cases. Again, I kind of tried not to do it, but this here. There are two cases. If psi of a and psi of b are non-zero, non-infinity, then that's just obvious. Because when you restrict yourself to non-infinities, you really apply the projection map, and the projection map is a homomorphism. So, yeah. Case two is, without loss of generality, psi of a is not infinity, but the other one is. Let's just do that, and let's check that in this case, both psi of a and psi of b, both this and that are infinities. Yes. Mm-hmm.
How can you, usually you can't define a field, right? So the statement, somehow you can define a field and then it's a relationally this field.
You can, which field, like this one or? Right.
Yes, so usually when you state statements like it is constant and then you can build the field. Now you explain the field. So I understand every line, I understand like story.
Not sure I got it. So like you're asking, you don't ask why is this a field, right? You ask, right? Yeah.
You understand like the statement that you don't say from the beginning. Right? You said that every place is a valuation.
Right. So good. Right. Exactly. So you have the freedom there. So I want to prove that, and actually maybe that's going to be the answer to the question. Give me two examples. But so you start with a ring, and I need to give you a place, and a place. In order to give you a place, I need to, and I have the freedom to choose any field I want at the outcome, any k.
Why?
To be any something particular. Yeah. It doesn't require it to be like the field like related to the ring in any sense. You can, right? I mean that's right. So here, right? So yeah, they're all kind of, so of the valuation ring, since in a big field which has nothing to do with it, that's the like field of rational functions. The field we are talking about is like F5 or something, right? The smaller fields that we get the residues from. Now, if these were the rational functions, you say, okay, over what field? And that should probably be the field, the residue field. But you don't have that. It's completely abstract. So you give me a valuation ring in some field, which you think of as fractions and stuff, but rational functions or whatever, but you don't know. And I have the freedom, like cooking up the place, I have the freedom to, I mean, I don't have the freedom, I have to start from F, the F that, these are the fraction field of these rings, but I can end up everywhere I want. I mean, that is to my discretion. Because a place of F is defined without any restrictions to this. I mean, having said that, the residue field doesn't care about K, just the evaluation of phi at F, excluding infinity. So the residue field is the kind of intrinsic to F, but K, you can add like weird elements to it and never send any function to it. So what I'm doing in there is actually taking the residue field. I'm taking the right K in the definition.
You have relationship, it doesn't live with any field, right?
Right. There is no like F5 there, technically speaking. There is no like F5. There is no like finite field. Right. So
Inside a big field,
exactly.
Figure is something like.
Yeah. Right. So in the large field of function, like for example, it has a characteristic, and it will give you some hint about what is the small field. Like if the characteristic there, you can ask, this is a field, what's characteristic of the field? And maybe I'll tell you 5. Then this means that this K should be like power of 5, really. That's the only thing that will make sense, because 1 has to go to 1 and so forth. But and it's a homomorphism. But other than that, you don't have any information. And really, it depends on the point. Like for different points, for different valuation rings, the answer would be either F5 or F25. It really depends on the point. For example, in the case of exactly. Yeah, exactly. So for example, x minus alpha in the rational function field, x minus alpha, it will map things to F5. But if you take an irreducible polynomial of degree 2, I mean, it's slightly premature to talk about it. It also gives you a valuation ring, and then the right answer here is F25, because you mod out by a degree 2 polynomial, so it's like F25. I mean, it's not obvious. I'm just giving the examples, not explaining why these are the right things I'm saying. But right, so the valuation ring doesn't. I mean, it determines in a very implicit way that we're writing there what is this field. And the implicit way is you should mod out by the maximal ideal. Which right, yeah. So, but in the examples that we did, we defined this to be an evaluation in the examples. So it makes sense that you can do it maybe in the abstract setting. So, given an abstract ring with a maximal ideal, maybe that's a good, and it's a unique maximal ideal, by the way. So it means that you don't really have a choice here, which is sign that you're doing the right thing, because there is no wrong thing to do. It seems like a good idea. So I'm cooking up this field. That's a good question, right? I'm cooking up this field from the ring, maybe following the motivation from the examples, but. I mean, this has to be a field because by definition of places. Yeah.
Why do you need it to be?
By definition of, I want to construct a place after all. So I need it to be a field. Right. And it is a field because it's a maximal ideal. Yes. Okay, so I just do the second case and that's it, just so that you're done with that. And so the second case, we're just checking that, in the case that one of them is infinity, well, we know the answer here, right? So if this is infinity and this is not infinity, then this is what? Infinity. So we just need to make sure that this is infinity. So we need to check that psi of a plus b is infinity. Indeed, otherwise, so proof by contradiction, otherwise, a plus b would, once again, no, I did something different. Yeah, no, otherwise. I mean, you can do it in several ways, but I better stick to the plan. So a plus b is, I'm claiming that that's true because, I mean, saying that is equivalent to saying that. That is equivalent to saying that, because R is exactly all of those things that don't get infinity. And but this is true because if a plus b is in R, so I want to contradict this, it's the same as contradicting that. If a of b were in R, then b, well, b is always this thing, that's just b. But if this is in R by contradiction, and because this is in R, a is in R because phi of a is not infinity, then b would be in R, which would contradict that phi of b is infinity. Right, that's the kind of annoying case analysis I didn't do in the other. Yeah, okay. So I have 2 more minutes, so I think I'll take those. No, like 1 more minute now. Good. So next time we are going to do the running example that we have, and then we are going to move to somewhat like more deep stuff. So we do the point. Okay, thank you.